Good morning, everybody. Happy Monday. I was reminded that your exam is a week from tomorrow. That's a good way to start class, isn't it? Way to kill a buzz. So let's see. That means that next Monday, a week from today, we will be doing what? The review, right? Which is where you come and ask me questions. Which means we have today and Wednesday to finish up chapter 27. Which I think we can do because we've got to do this example and then I've got to teach you something called Kirchhoff's laws. And we'll be pretty much done with chapter 27. So we might even have a little bit of extra time to do homework on Wednesday. We'll see. But that's kind of the next 8 days in a nutshell, right? So be ready. I will get the topics list to you for the exam as soon as I finish writing the exam. I got part of the way this morning. All right. We left off here last Wednesday, but that was last Wednesday, right? Does anybody remember any of this? Yeah, no. Thank you, Nico. But let's do the whole enchilada, right? Let's just kind of back up and make sure that we see the whole process when it comes to circuit analysis. This is what we're doing. We're trying to puzzle out everything that we could know about this collection of resistors. And the way we're going to do it is we're going to simplify this circuit down to its theoretically most simple case. And then we're going to explode it back outwards. And as we explode it back outwards, working our way backwards through our simplifications, we will find out what's real about each of these real resistors. And by that I mean we are going to use this table over here. I'm just going to go ahead and grab this table because all of this stays the same, so I might as well just keep it. Which one's the copy button? That one. Okay, so I'm just going to pull that over to save some time. Again, what's that little spreadsheet there for? Keep track. I honestly feel like the hardest part of circuit analysis is keeping track of what you have, where you are, what's real and what's an equivalent resistance. Conceptually, this is nothing like Gauss's law, where you're just kind of at sea about imaginary stuff, right? We have real physical things we can point at, and then we have combinations mathematically that we're putting together. But it's keeping track of where you are and what you're doing and what you know. It can be very hard. And so this is something that helps me. It may or may not help you. Maybe write on the diagrams that you draw helps you, whatever. I kind of have a mixture of both in my style. But it's no surprise electrical engineers came up with computer models and simulations to do this for them a long time ago. But anyway, we don't have that, so let's just go. Our first combination, the first simplification we'll make, where do we start with respect to the battery? As close to or as far away from? As far away from. Get as far away from the battery as you can and start kind of working towards the battery. And as we saw before, R2 and R3 are in what? How do we know they're in parallel? There's junctions there, right? The wire that comes into 2 and 3 splits, goes through, and then comes back together, right? So we know that those are in parallel. It looks like 2, 3, and 4 are parallel with each other, doesn't it? Just because of kind of how they're drawn in the thing. But, could I have drawn R4 right here instead? Sure. There's no difference schematically between the connections. I draw it that way. So don't rely on the actual physical location. Look at the junctions. Look at what are happening to the wires. All right. So I like to use colors when I can, but I like to kind of draw a box around what I'm doing and then do my equivalent resistance calculations. That's 1 over R2 plus 1 over R3. And then the equivalents, so I better do it down here so I don't run out of space, are equivalent. If I invert that side, I got to invert the other side, right? So 1 over 2 plus 1 over 3. Why is it 1 over 2 and 1 over 3? I set this problem up so that the label is the resistance. In your homework, they'll give you like 130 ohms, right? You have to put in the resistance of the resistors there. All right. And we found this to be 1.2 ohms, right? So that combination. And so my new picture now is a battery with R1. And then like this new resistor that's right here. There's a junction right there. That goes to 5. So now I've got my 1.2 ohm, and that's connected to the 4 ohm like that. So the 1.2 and the 4. Excuse me. I thought there was another one coming. They usually come in pairs. I used to. That was actually a pretty quiet one. I usually sneeze much louder than that. Yeah. In graduate school, we were in these offices, and our offices had these metal shelves for holding all of our books. But we were graduate students. We didn't have very many books compared to like our teachers. So the shelves were typically kind of empty, or empty-ish. When I would sneeze, my sneeze would match a resonant frequency for the harmonic of the bookshelves, and they would start to like sing and ring when I sneezed. And so one day the acoustical guys brought in a microphone to clock one of my sneezes. They wanted it recorded, and then they went and found that I was getting pretty close to the speed of sound as through my vocal cords. We would do anything at that point other than do our homework. All right, so what 1.2 and 4, what is that? That looks like a series connection, doesn't it? Right? So we put these two together in series. That equivalence 1.2 plus 4. So that gives me 5.2 because I can add sometimes. Never. Okay. So now what does my drawing look like? If I'm going to need space, so we'll do it down here. It's going to look like a 1 ohm connected to a 5 ohm with a branch that's got a 5.2, 5 and 1. So next combination. Let's go to this parallel combination right there. So my equivalent is going to be the inverse of 1 over 5 plus 1 over 5.2. So, and I did that. I got 2.55. Again, we did this all last Wednesday, but I wanted to, again, show you the whole process. And it's good practice. Okay, that leaves me with a drawing. Battery 1 and my 2.55. So now my equivalent resistance will be 1 plus 2.55 or 3.55 ohms. So we made it to the end, right? We made it to a circuit that looks like this, where this is a 3.55 ohm resistor connected to a 15 volt battery. And we're 1/3 of the way through, right? That simplification and so on and so forth. To begin to work backwards, and when I mean like step 1 is simplifying the circuit down, step 2 is working backwards, applying Ohm's law at every step. Ohm's law, V equals current times resistance. We look at our simplified circuit here. What are the two things that we know? Voltage. So what's the thing we don't know? Find the thing we don't know for this really simple circuit. Okay, the thing we don't know is the current, which is the voltage divided by the resistance, right? If I rearrange Ohm's law. So that's 15 volts divided by 3.55 ohms, which, when I do that, gets me 4.23 amps. I knew I wrote it down somewhere in my paper. Okay, so that current right there is like that is the current that is coming out of the battery. How do I know that that's the current coming out of the battery? In this simplest form of the circuit, I have two elements, right? And they are in series with each other. The battery is in series with this resistor. So current flows out, goes through the resistor, comes back to the battery. 4.23 amps flows through this battery and through this 3.95 ohm resistor. But that 3.95 ohm resistor, or 3.55, whatever it is not a real resistor. It's a mathematical resistor. And so what we want to do now is we want to back up to our next simplest diagram and take a look at what we did here. What happened? How did we combine these two resistors together? In series or in parallel? Okay. Sometimes it helps if you actually write down what you did. Series, right? Parallel. These were in series. And this one was parallel. Should have left myself little notes as I went through. Okay, so that's in series. What's true about resistors in series? What do we know about voltage and current about resistors in series? Current is equal, current is the same, and voltage is split up or shared. If something is shared, not everybody gets the same amount. I mean, typically, like they teach you in kindergarten, sharing is caring, right? And you're supposed to, if I have 3 apples and 3 friends, I split them up and I don't get an apple. Well, I don't know how that works, right? But when we say voltage is shared, it means it gets divided up and doesn't have to be equal, okay? But when we say current is the same in series, what we're saying is it is the same number all the way through. We don't have to divide that thing up. So with current, yeah?
Quick question. Why is the 1.2 and 4 a series, not a parallel?
There is no junction between the 1.2 and the 4. In other words, I can go through the 1.2 and through the 4 and never meet a junction. Are you looking at these over here? Yeah, right? But there is a path I can walk where there's no junctions. And that's how you know they're in series, right? But like the 1.2 and the 5 are definitely in series. The 4 and the 5 are in parallel, right? Because there's a junction there, right? It's just we can't really combine them because like these two are both in parallel simultaneously. So we want to get them together first before we move and start doing that. And it looks like they're in parallel, doesn't it? It's tricky. But yeah, we're looking like I can see that there's a path through this one, but to get to this next one, I have to go through a junction, this junction. So that means that these two have to be in parallel. So think like an ant. Think like you're walking along and you go through like, okay, but junction. Can't be in series. And I generally try to find all the series ones first, if I can, right? Like if there were a resistor right here, I would have combined these two first because they're in series. But that's just me. Good question, I like it. Okay, so since we added in series, it says it right there, that means that the current has to be the same through the 1 and the 2.55. What's the current through the 1 and the 2.55? It's 4.23 amps, right? 4.23 amps is what's coming out of this battery and goes through the 3.55. But I still have a series connection right here. And so the current has to be the same. That means that the current through my 1 ohm, this is my 1 ohm resistor, the current through my 1 ohm resistor is 4.23 amps. Can you guys see that gray okay? And then, it didn't give you a chance to answer. And then the current through this one, I'm getting messy now, is 4.23 amps. So, have we discovered anything about a real resistor? An actual physical resistor in our circuit? Which resistor? Number 1, right? So that means we can come over here to our table, okay? What have we figured out? We figured out that the current was 4.23 amps, right? All right, look at what we've got. We've got 2 resistors, we know their resistances, and we know the currents through them. What's the missing thing? Voltage. So how do we find the voltage? It's I times R, isn't it? It's going to be 4.23 amps times 1 ohm. So again, amps, 4.23 volts. So this is 4.23. Okay, and we do the same thing for the 2.55. The voltage is going to be the current, 4.23 times 2.55. 10.77. I can't put anything in my table, right? Because the 2.55 ohm resistor is not a real resistor. It's a mathematical resistor. It's an equivalent resistance that came from something, right? But now that I know the voltage and current through that 2.55 ohm resistor, where did the 2.55 ohm resistor come from? It came from the parallel combination, didn't it? And what do we know about parallel? What are the rules for voltage and current in parallel? Voltage is the same. They are the same number. Do we know the voltage? Yeah, it's 10.77 volts, right? We found the voltage through the 2.55. That has to be the same across each of its things that went into it, which means that I have a 10.77 volts across that 5 ohm resistor as well as a 10.77 volts across the 5.2 ohm resistor. Do I now know something about a real resistor? Yeah, the 5, right? I have 10.77 volts. So how do I find the current of that? Voltage divided by resistance, right? 10.77 divided by 5 is 2.15 amps. And then do the same thing over here. 10.77 divided by 5.2. I'm getting messy. 2.07. Come up with a better method than me for organizing all this information. Okay, so I have 2.07 amps going through that 5.2 ohm not real resistor, mathematical resistor. But that 5.2 came from somewhere. Where did it come from? Came from the series combination of the 1.2 and the 4. We know the current, so that current has to be 2.07 amps and 2.07 amps because the current is the same in series. What's happening here? It's Ohm's law and it's the rules, like the what is the same and what is shared in parallel and series. So conceptually, you need to hold in your head Ohm's law. You need to remember that for a series connection, current's the same. And for a parallel connection, voltage is the same. and apply those rules at every point of your circuit. Is it hard to divide 10.77 by 5.2? No. So what's hard about this? Keeping track. It's keeping track, right? Because how many times do you have to take a current and divide by a resistance? A lot. And how many times do you take a current and multiply by the other way around? Voltage divided by resistance to get a current, but then you have to sometimes take a current times a resistance to get a voltage. And do you see how quickly this can become confused in your head? Am I multiplying? Am I dividing? What the heck is going on? Your brain works differently than mine. Some of your brains work the same as mine, whatever, right? Doesn't matter. Come up with a method that helps you keep track of what you are doing. I've watched students have to, like, on separate pages, draw each of these simplified things, right? Just so they have enough room, right, to keep track of everything that's going on. I've seen students do it in spreadsheets. You've got to be able, on the exam, you want to have a spreadsheet, so you've got to be able to show me, right, that you know how to reduce a circuit, find out what's going on in the circuit, right? So just be aware of that. I've broken it out into several steps. Some of you might feel comfortable with going, oh, well, I know I've got like maybe even the blue and the purple could get smushed into one. Be careful about doing that, because if you start doing too many steps at the same time, you start losing what current you might know and all that kind of stuff. So it can be really hard. Question? Did I write? It's messy, isn't it? Yeah, I shouldn't have done it the way I did it. Let me do this over here. Between these two, right, it's 10.77 volts divided by 5.2 ohms. And that's 2.07 amps. Did I get that right? My math could be very off. I don't know. Pretty good? All right. It's just a number. Really don't care. Okay. But now that I know both the resistance and the current, I can find out the voltage of my 1.2 and my 4. For my 1.2, the voltage is going to be the current, 2.07 amps, times my resistance, 1.2. So that's going to be 2.48 volts. And for the voltage on my fourth, it's going to be the current, 2.07 times 4. Oh, that's a real resistor, isn't it? 2.07 amps, and I got 8.28 volts for that one. All right. Oh, can I please be done? One. Okay. So what's the last one that's not real? It's this one right here, isn't it? The 1.2. And it was a parallel combination, wasn't it? So what's the same in parallel? The voltage. What's the voltage that I have for the 1.2? It's 2.48 volts, isn't it? So both of these have 2.48 volts in the 2.48 volts in them. And now I can just do to find the currents, V over R. And when I do that, I got 1.24 and 0.83. So I have found the voltage and current for all of the real circuit elements in this circuit. To calculate the power, how would I find the power in watts? Yeah, it's just current times voltage the whole way through. I'll just do that. 17.8, 3.08, 2.06, 17.1, and 23. All right. How do you possibly check this? I mean, look at this thing. Somebody barfed Ohm's law onto the screen, right? Like, this is a mess. How many? There were like 15 different divisions and multiplications in there, or 25. Like, there's just a lot, wasn't there? How do you check? What should, just take a guess, what do you think all the voltages should add up to? What do we start with? 15. Shouldn't the voltages all add up to 15? No, they don't, because 10 plus 8. Should the currents all add up to 4.23? There's branches here, right? Parallel and series, and things split up and do weird stuff. So, but energy has to be conserved, right? So where is energy conserved here? What is the one thing we can add up and check? It's the power. Because the power dissipated by the circuit has to be the power that the battery's putting out. The voltages don't add up unless we're really careful, okay? Because the 8.28, right, is those two numbers put together, isn't it? It's voltages that split and then come back together again. So to get it right, we'd have to go through and it gets weird, okay? Same thing with the currents because of the splitting and the recombinations, okay? The current through 2 and 3, right? That current splits up after 1 and 5 and then recombines before it comes back to 4. So keeping track of those currents and voltages, again, very difficult. But power-wise, energy must be conserved. So how do we find the total power in the circuit? Well, we can go through and just add up all of these powers and get 63.4 watts. But is there a different way for us to find the total power?
Total voltage and total current.
Yeah, we know the power is equal to current times voltage. If we use the total current, 4.23 amps, and the total voltage of 15, and we multiply those things together, we get 63.45 watts. So within a round-off error here, we got the same power. And so that's a check that can be performed if your circuit consists of nothing but resistors. Okay? If power is being consumed, if the battery is putting out current and voltage, whatever that power is what the circuit uses up, regardless of its series and parallel connections. So that's typically something I'll do even if I'm not asked to do it. I'll check to make sure my powers add up. Let's talk about something more practical that's going to be what you're going to be up against on Tuesday, right? Because of the exam. How do I test this? Right? Give you one problem, right? This one, right? Okay. Good luck. Let's see if you can make it. No, that would be terrible. Okay. So what I've done on the exam is I've kind of divided. This is what I typically do on this exam. I kind of divide it up. So you'll have questions where I ask you to simply reduce a circuit. Like, what is the equivalent resistance of this combination of resistors, right? So basically, you show me that you know how to add series and pair, right? And then maybe instead of asking you for all of this information, I have a different problem that's perhaps a simpler circuit that takes less time. But like I ask you, like what's the current through the first resistor, right? It requires you, yes, to be able to collapse it down, but then in the working backwards, you really only have to work one step, right? So like, I've tried to make every problem on the exam be an average of 10 minutes, right? So I'm thinking, okay, as a student, in 10 minutes, would you be able to collapse this down? Okay, that's a problem, right? But then as a separate problem so that the problems do not depend on each other, right? Even if you miss one, you can still get the other, right? You have a different circuit that I'm asking you, okay, here. And maybe, like, I can kind of simplify it a little bit by, like, maybe telling you the current in one of the branches, right? That would just make it go just a little bit faster. There's little tricks I can do to make it go quickly, right? So that you're not getting, like, all of this and have to chug through an entire circuit. So I'm trying to communicate to you that I've set up the exam to be able to test you on the different elements of these things, right? And hopefully help you save some time. Yeah?
There is no way to go from the final circuit, the collapsed one, to find like elements of resistor 1? Like you have to go through the whole thing?
Pretty much. I mean, the nice thing about a resistor 1 here is that it is a real resistor in this first backward step, right? So boom, there, okay. Now I know the current through it. Now I can,
So like 2.
Right, you kind of have to do 2 steps back, right? It'd be really mean of me to say, what's the current in R2? I wouldn't put it past me, but like that would be really mean. And if you see that, you're like, okay, that's the last problem I do on this exam, right? Because all of the problems are the same value, aren't they? So get the ones done that you can get done fast and save the slow ones for later. So yeah, I guess what I'm trying to communicate to you is, yes, you're going to spend a lot of time on your homework trying to get through some of these problems, right? Trying to keep track of everything. I understand that on the exam, I'm not going to expect you to like do something this big. Okay, yeah.
Are we gonna have one like there was a question on homework was like the cone that like
No, I threw that one on there so that you guys don't forget how to integrate. Because guess where integrals are happening again? Next Wednesday. Yeah. Have you been enjoying your vacation? It's like, this is the vacation? Yeah, it's the vacation. All right. Here's the problem. The circuits I've shown you so far, while possibly real, aren't that real. What do I mean by that? There aren't a lot of circuits where there is only one battery or source of electrical energy. Sources of electrical energy can come from a lot of different places. It can come from a battery, but it could also come from a wire, like a charging circuit plugged into the wall. Circuits could have multiple batteries and power supplies in them for doing different things. And so it's not unheard of, okay? But you could have a circuit like this one. This is, so here's a resistor, and we're going to call it a 30 ohm resistor. And then I'm going to connect that to a battery right here that's a 45 volt battery, connected to a 21 ohm resistor and a 20 ohm resistor. And then there's another branch down here with a second battery in it with a 10 ohm resistor and an 11 ohm resistor. So that's a potential circuit that highlights a problem in that there are now 2 batteries, 2 sources of electric potential in this circuit. And you're like, Mr. Balogh, why would you ever do that? We'll talk about what this actually represents kind of a real circuit. I'll explain what real circuit it is later, okay? But let's just fall back on what we know about series and parallel and see if we can't simplify this circuit. It's like first step, right, is to always go for things that jump out at you right away that you can guarantee this is series or parallel. Is there anything that jumps out at you? The 20 and the 21? What's true about the 20 and the 21? How do you know? If I'm an ant walking between each of them, I can get from one to the other without going through a junction, right? So we could redraw this circuit with the 30 up here, and then this 45 volt battery, and then like a single resistor. But then what's the other one that's in series? The 10 and the 11, right? I can just draw it right there. So this would be a 21 ohm, and this would be a 41 ohm. Did I add correctly? Yes. Okay. Now what? Are there any other combinations? We got to get down to the simplest circuit we can, right? Are the 41 and 30 in parallel? I mean, yeah, there's a junction between them, right? But parallel and series are defined, really, with reference to the batteries they are connected to. Series and parallel with what? Well, if we ignore the bottom branch and we look at the 45 volt battery, are 41 and 30 now in parallel with that battery? No, they'd be in series, right? But if we look at the, I forgot to tell you what this is an 80 volt battery. Okay. If we look at the 80 volt battery, then 41 and 30 are in parallel with the 80 volt battery, aren't they? And the 21 and 41 would be in series with it. It's like we've got both series and parallel depending on which battery we're talking about. And so this turns out to be the simplest circuit that we can draw. So now we've got a problem. Our problem is our simplest circuit isn't very simple. We can't get down to like a single equivalent resistance, which we can then try to work backwards with to find out the current and voltage through all the elements in the circuit, which is where Kirchhoff's rules come into play. Kirchhoff was a dude who, well, actually, he didn't really discover anything. We used to call these Kirchhoff's laws. And the reason that we've changed the language to rules is because Kirchhoff restated two conservation principles that were already laws. He just redid them in the language of circuits. Okay? And so Kirchhoff's rules, two of them, okay? I'll tell you what they are, and then we'll play a guessing game as to what conservation laws they apply to, okay? Kirchhoff's first rule is called the junction rule, okay? And what he said was whatever the current flowing into a junction is, that has to be the current flowing out of a junction. In other words, if 10 amps splits up, you can't get 15 amps out of the split, right? If 10 goes in and 7 goes down one wire, what does the other wire have? 3, right? It's not going to have 4, it's not going to have 5, it's not going to have 2. Whatever current went into a junction has to be the sum of the currents going out of the junction. So really, you can kind of think of that as there's a sort of a summation symbol in there if you want, okay? But whatever amount goes in has to be the amount coming out. Kirchhoff's junction rule. The second, called the loop rule, states that for a closed loop of the circuit, in other words, an imaginary path through the circuit where you start and stop at the same point, the total sum of potential changes has to be 0. So in a simple circuit, in a really simple idea, right, consisting just of a battery and a resistor. If this is a 10 volt battery, okay, a charge gains an electric potential of 10 volts moves through the circuit, and what does it have to do across the resistor? It's got to lose 10 volts. Remember, batteries are like pumps, and resistors are like waterfalls, right? So if it gains 10 volts, it has to lose 10 volts. And no matter where we start, if we start down here in this corner and we walk around, adding up all of our changes in potential, 10 plus a minus 10 is what? 0. If I start up here, negative 10 plus positive 10 is 0. No matter what I do, right, I have to have a total potential change of 0 for a complete walk around a loop in my circuit. Have you figured out what the second rule is? It's conservation of fill in the blank. No? Voltage is electric potential, which is very closely related to electric potential energy. So what is Kirchhoff's second rule a restatement of? Conservation of energy. Whatever energy a charge is given, it has to lose it by the time it gets back to the battery. It's got to go somewhere, right? So it can get pumped back up again. So the second rule is a statement of conservation of energy. It's written in electrical terms, written in terms of voltage. So anybody figured out what the first rule is, the junction rule? It's conservation of blank. Fill in the blank. It's the other conserved thing that we have learned about in this class, pretty much day one. Charge. The junction rule states that you can't make charge out of nothing. Okay? Whatever charge per time flows into a junction has to equal the total sum of charges coming out of that junction. So, if it isn't, you've lost a charge somewhere, and that's not good. So that's why they're called rules nowadays, Kirchhoff's rules. You might still find some places that call them Kirchhoff's laws. They are based on physical laws, conservation of charge, conservation of energy. They're just restatements of those things in other terms. Okay, to be able to apply Kirchhoff's rules consistently and correctly, there is a predetermined set of conventions that are used. This is the electrical circuit equivalent of defining a coordinate system. So let me walk you through the 4 conventions of Kirchhoff's rules. With Kirchhoff's rules and these 4 conventions, we can do any circuit that is thrown at us. The conventions are this. Do I have it separate? I don't. Okay, quiz coming up. They consist of, and I'm going to write them down. They're not going to make a whole lot of sense. Just bear with me, okay? In all 4 conventions, we are looking at what's going on in a resistor or a battery. I did that totally wrong. I drew 4 resistors. Resistors or batteries. There we go. Got it right. Okay. And what we're looking at for resistors is current direction and loop direction. So with current flowing one way and our loop, and we'll talk about what a loop is and how to identify these currents here in a second. But notice, if the current and the loop direction are the same, we are going to define this change in potential as a negative. This is the standard way that we think about resistors. If a charge goes through a resistor and goes downhill, we call that negative, right? It ended up negative voltage. If our loop direction and so I'll keep the loop direction the same here, but our current is opposite the loop direction. And here in these conventions, it doesn't matter what the actual directions are. All that matters is if the directions are the same or opposite of each other. If the directions are the same, for example, if they're both pointing to the left, then it's a negative IR. But if they're opposing each other, then it's going to be a positive IR. It's as if the charge is trying to go up a waterfall. Equals positive IR. Again, these are conventions. They're agreed upon standards so that everybody in the world can talk about the same thing. If we don't lay this out, then there's just going to be general confusion over which way you're calling positive. Worked on my screen. It lagged. Okay. There's no such thing as lag. All right. For the battery. We know big side of battery is positive, right? And small side is negative. If the loop is taking you through the battery in what I like to call the normal direction, the regular direction, from negative to positive side, pumping a charge up, we're going to call that a positive voltage. You want to take any guesses as to what happens if the loop direction is opposite? It's negative. In other words, if you're walking around a circuit like an ant running along the wire, and you happen to go through a battery backwards from its positive to its negative terminal, you're really kind of going downhill. You're like everybody's riding the escalator up. All the charges are riding the escalator up, but you're the charge that's trying to get backwards down the upwards moving escalator, right? So you're going negative where everybody else is going positive. So this whole set right here is what allows us to handle complex circuits. These rules applied with those conventions allow us to figure out very complicated circuits. So before I do the example that is this circuit on the screen and tell you what it is, let's do a quiz. Let's make sure that you are handling this concept and idea of Kirchhoff's rules and the conservation principles that undergird them. Let's apply our rules to our circuit here and see what we can't come up with. So I think what I'm going to do here, let's get a page in, and then let's copy paste some stuff. No, let's not do that. Let's do this. We'll put our conventions over here, and then we'll take our circuit. Don't you love it when people narrate copying and pasting? There we go. We'll put that right up there so we can do this in full. So I've got my conventions off to the side so I can reference them, and I've got my circuit that I'm working with over here, and we'll just kind of block this out. All right. So what we do when we analyze a circuit is we have to make some choices. And quite frankly, a lot of this is a guess. And as long as we stay consistent with our choices, it's going to work out, even if physically it's backwards from what we pick. And I'll explain that in a bit. For the purposes of right now, okay, I'm going to label the junctions of this circuit. This is not necessarily something you have to do, but I want to, here in class, be able to guide you through. And it gets a little bit hard saying the left-hand junction and the right-hand junction, all that kind of stuff. So I'm going to label the two junctions in this circuit. I'm going to label this one junction A and this one junction B. Okay? Again, I'm just doing that to make it easier for me to reference what's going on. I'm going to start at A, I'm going to start at B. Just an easier way to go about doing it. Kirchhoff's analysis, the steps that you have to go through involve, number one, figuring out how many unique currents there are in your circuit. Step 2, figuring out how many loops there are in your circuit. And step 3, applying the rules. So first step, how many unique currents are there in the circuit? The way to do this is to look at any junction. The number of wires in that junction is the number of currents, minimum, that you have in the circuit. So let's look at junction A. How many wires are going in and out of junction A? 3. There's 3 wires. Okay? There's a wire from the 80 volt battery, there's a wire from the 30 ohm resistor, and there's a wire from the 41 ohm resistor, right? There's 3 wires coming together at junction A. That means there is at least 3 unique currents in the circuit. There could be a current, and the direction we pick, okay, makes absolutely no difference. You just have to pick something. Unless you're told in the problem. Sometimes in the homework they tell you the current is this way, and then you have to kind of follow what they chose, right? So that your signs come out the same as theirs. But in general, you get to pick the direction of the current. There's a current in this middle branch. There's a current, and I'm just going to say it flows that way. Again, I get to pick. I just get to pick. It's my choice. And then I'm going to say there's a current in this branch. So those are the 3 branches that I have. And now we need to label them. And I'm just going to label them I1, I2, and I3. Again, it really doesn't matter which order you pick these in. What matters is that you give them a label and a direction. And the direction is your choice. Personally, it just helps my brain. The reason I picked I2 going to the right in that bottom branch is because I like to look at the battery, right? Batteries cause potential and charge to flow, right? So the battery's going to be pushing to the right down there, isn't it? So I just went with the battery. Same thing with the middle branch, I3. I just kind of went with the battery. Now, with the top branch through the 30 ohm resistor, there's no battery up there. So I just was like, whatever, up, right? It doesn't matter what actual directions you pick. All that matters is that you pick a direction. And once you do, you stay consistent. You don't reverse it halfway through your problem. Because if you start doing that, you're just going to be lost. So first step, figure out how many currents you've got, draw them into the diagram with directions. Give them some labels. Again, the purpose of this is to figure out everything there is to know about the circuit. I want to know every voltage and current running through everything. Yeah?
Wait, are you placing the arrows based on where the resistors are or where the batteries are?
I'm placing it based on where the branches are. There is a unique wire branch of the circuit that's along that wire. So I could have drawn it anywhere along that wire. And then there's another one up here. So current 1, even though I drew it, going upwards here, it's going to the right and then down, isn't it? It's got a flow that goes in basically what looks like a clockwise direction. Okay? And then down here, I've got another branch. It's just, I put the label here. I could have put it over here. I could have put it down here.
So you're just using the 3 different wires?
Yeah, the 3 different wires. Because the junction comes together. Now, look at the other junction, junction B. How many wires are there at junction B? 3. So you know that there's at least a minimum of 3 possible new currents. But are there any new currents? Are any of the wires at junction B any different from any of the wires at junction A? No, they're all just kind of coming back together, right? So I don't need to worry about that.
If you have, let's say, a different problem where one junction has 4 connections and one has 5.
Then you know there's a minimum of 5 unique currents. And there's probably more. Yeah. It could be less. It depends on how the wires come back together. But yeah, I usually go for the worst case scenario, and then I'm really happy when I find out that it's not. That's just a way of fooling my brain. Okay, so with those currents figured out, we can now write down the junction rule. So junction rule, junction A. What currents are flowing into junction A? Look at the direction of the currents. Which currents, current or currents, are flowing into A? Just I3. In equals out. What currents are flowing out? I1 and I2. That's the junction rule. In order to write it down, you do have to assume, you got to guess some currents, their directions, so you can write in equals out. All right, let's do junction B. What currents are flowing into junction B? 1 comes in, doesn't it? I1 flows all the way around in this part of the circuit and comes into B. What does I2 do? Also goes into B. So the ins are I1 and I2, and what's flowing out of B? Yeah, I3 is coming out that way, so I3. And notice, those two equations are the same equation, right? So generally, you don't have to write down all of the junctions. It's safe to, but you'll probably end up repeating equations, right? So there isn't really a unique equation there. They're the same equation. It is what it is. Let's do the loop rule. Okay? So for the loop rule, we need to find the total number of closed loops, paths where we can start and stop at the same place and have done a full loop of the circuit. There is not one, nor is there two loops in this circuit. How many total loops are there in this circuit? 3. Huh? There is a loop here at the top. I'm going to call it loop number 1. And then, there's a loop down here at the bottom, isn't there? And by loop, I'm literally like, if I start at A and I come around and I get back to A, I've done a whole loop, right? So number 2 would be down here. And I'm done, Mr. Balogh. I've run out of loops. Where's the third loop? It's around the outside. Don't forget the outside one. So we'll make the third one around the outside. Okay. When you identify your loops, again, you need to pick directions with those loops. Clockwise or counterclockwise. Doesn't matter. But once you pick it, stay consistent. I'm going to pick clockwise for number 1. I'm going to pick counterclockwise for number 2. And I'm going to pick clockwise for number 3. I've drawn arrows on my loop indicators that are trying to indicate the direction I'm calling positive. Number 2 there, I drew the arrow so that it's going counterclockwise, but 1 and 3 are both clockwise loops. It's like a loop orientation, if you will. Okay? So now that I've done that, I can apply the loop rule. And I've got 3 loops. I got loop number 1, loop number 2, and loop number 3. Okay? I do like to start with 0. 0 equals 0 equals 0 equals. It's kind of like the way I do Newton's second law. I like to start with MA first and then figure out what my sum of forces is. I like to start with 0 equals and then figure out what my sum of voltages is. Because if I concentrate on the sum of voltages, I often forget what it equals. Like, what is it equal to? If I start with that, I'm less likely to forget it. Okay, so loop number 1. We want to go around loop number 1 and figure out all of the voltage changes that we run into. And as we do so, we're going to apply our conventions. I'm going to start at point A. Doesn't matter where you start as long as you get back to that point. But I'm just going to start at point A. And I'm going to imagine I'm a charge flowing along the wire, or an ant locking along the wire. And what's the first circuit element that I get to? The 30 ohm resistor. And I have to decide, what is the voltage in that 30 ohm resistor? Well, if it's a resistor, the voltage is going to be the current times the resistance, right? But the resistance, I already know what the resistance is. It's 30, right? But what current is in that branch? It's I1. But now what is the sign? Positive or negative? Now we look at the direction of the current and the direction that we are walking. What direction are we walking? We are going to the right or clockwise, aren't we? What direction is the current? Is it same or opposite? It's the same direction. So what are we going to write down? Negative sign. The convention is that if your loop direction and your current direction are in the same direction, you write down a negative sign. So I'm going to put a negative sign in front of that one. Okay, we're walking along. We've gotten to 30. Now we get to B. We've got to hang a right-hand turn here. Now we're going through a battery, aren't we? So as we go through this battery, what direction are we going through the battery? Is our loop taking us from the small to the big or the big to the small? We're going up like what I think of as the forward direction for a battery. Our charge would go from the small plate to the big plate and gain energy, wouldn't it? Gain potential. So what are we going to write down? Positive 45. Okay. What's our next element as we continue our circle here? It's the 41. What way are we walking and how does it compare to the current? Same direction. So what are we going to write down? Negative I3 times 41, right? Since we know the resistances in this problem, it's the currents we don't know. The currents are unknown to us. Okay? And so those are going to be the things that we're going to go solve for. All right. Write down loop number 2 right now in your notes. Start at A, just so we all have the same starting point, and work your way around counterclockwise. Again, asking yourself the question, am I going the same way, opposite way? See what you can get down in a minute or so. If you're stuck, call me over right now. All right. How am I doing so far? I started at point A and I got to the 80 volt battery. How'd I do on my sign? Are we good? Why? My loop direction is taking me through the battery from its negative to its positive side, right? So that's plus. All right. Current and loop through 21. Same or different? Same, so negative. Okay, got the negative on there. And then I get to B and I turn and I go through the battery in the forward direction, so that's positive 45. And now I get to the 41 ohm resistor. I3 is pointed to the left. I'm walking to the left, so what am I going to write down? Negative I3 times, what was it, 41? How'd you do? All right. Ooh, now what? It's the outer loop. Let's start at point A again, just because. So for the outer loop, coming up, we go through the 30 ohm resistor. Positive or negative? Negative, well, better, negative I1 times 30. Then I get to B and I keep going. I don't turn. Right? I'll go up and I'll come around, come to B, come down, and uh-oh. What direction am I walking? Opposite the direction the current's flowing. So this becomes positive. Positive I2 times 21. And then as I'm going through the battery, I'm going backwards to the battery, aren't I? Hit the big plate first. So what am I going to write down? Negative 80. And then that gets me back to A. And I'm done.
We have written 3 backwards. So like gone to the...
Yeah, if we had reversed I3. Is that what you're asking? No.
The loop
For
3.
loop 3.
Could you change its direction?
Oh yeah, could I change loop 3's direction? It's totally, you can choose the directions of the currents in the loops. Once you've chosen the direction, don't reverse it though, right? Yeah, we could have done 3 the other way around, and then we would have ended up with positive starting at B, positive I130, positive 80, and negative I221, which is exactly the same equation, just multiplied by negative 1. All right, what do we have? We have lots of equations. I'm going to rewrite number 1 here just to clean it up. This is 0 equals negative 30 I1 plus 45 minus 41 I3. Number 3 is 0 equals negative 30 I1 minus 80 plus 21 I2. And then I have an I3 equals I1 plus I2. The reason I wrote those 3 down is because they form a unique set of equations. I could use number 2. It would have been just fine. It's got I2 and I3 in it, right? But I have 3 unknowns, don't I? I1, I2, and I3. And I need 3 equations to solve for them. So pick any 3 that have at least a mixture of I1 and I2 and I3 in them to solve. I picked those. How do I solve this? This is a system of equations. I will show you how to solve that system of equations on Wednesday. Right? For those of you that have taken linear algebra, you know how to do this. For the rest of us, I will show you tools on how to do this. And you've already done it. See if you can't figure out where you've already done it in this class. See you tomorrow for lab. Be prepared to be frustrated tomorrow. You're dealing with real circuits, and they're frustrating. So just breathe deep.